Hello everyone, today we are going to talk about how to calculate the density of metals with hexagonal closed pack or HCP structure. This video explains key features of HCP crystals, derive the ideal fractions of C over A, um, and calculate the unit cell area and the volume, and applies the density formula using case study, for example, magnesium as an examples, and we compare theoretical values with the real density to show how closed pack structure or HCP geometry affects these results. Okay. At the left side, you see HCP, the hexagonal closed pack structures is one of the most important crystal structures in metals. We have many common metals in crystallized in HCP, such as magnesium, titanium, zinc, zirconium, beryllium, cobalt, and different materials in HCP. Each atom in HCP has coordinations number of 12. For example, you consider these atoms. What is the coordination number in neighbors? 1, 2, 3, 4, 5, 6, and 3 above. Exactly, we have 3 in lower surface too. So each atom in HCP has a coordination number of 12, 6 neighbors on the same basal planes, 3 are in the layer above and 3 on the layer below. Okay, the unit cell contains 6 atoms again. How we explain or derive N? We have 12 at the corners, right? Each of them common in 6 cells, 3 in same or same height and 3 above. So should be 12 times 1 over 6 for the corners. For the center of the surfaces is common in 2 cells, so plus 2, we have 2 at the surfaces and at the center of surfaces, and common in 2, so times 1 over 2, and we have 3 that 100% I show by blue color. Sorry. 3 inside that 100% belong to this cell. So totally it should be 2, 1, 3. So what is the number of cells in each number of atoms in each unit cell? It should be 6. So the unit cell contains 6 atoms in total because of this efficient packing that we have. The atomic packing factor or APF that we talked about that before in previous videos is 0.74 and same as FCC structure. Okay. In this slide, we want to find the optimum C over A ratio in HCP. The geometry of HCP unit cell is defined by 2 lattice parameters. The basal plane dimensions that I show it is A, all of them, all of these sides is A, it's the basal, and the height of that is C. Okay, for the perfect close packing ratio, C is about 1.633, but how we derive that? Look at this. It's a sketch of 1/3 of HCP. I show how it is 1/3. Look at this. It is part 1. It is part 2, and it is part 3. So it is part 1 only. it is part 1, and the height, that is C. Okay, consider this atom. It is M. Connect M to this. It is J. For example, it is L, and it is K. And you see here, M connect to J, connect to L, connect to K, and we have the tetrahedral section here. And the height from M to JLK surface, we considered H. Okay, we know that JM is A, MK is A, JK is A. And all of them equals 2R. Why? Because A direction is the more compact direction, and we considered in ideal condition equals to R, and R is the radius of the atom. Okay, in these triangles, triangle M, H, J. In this triangle, Jm squared equals Jh squared plus Mh squared. Mh squared, look at here, it is approximately half of C. So it is C over 2 squared. JH, we don't know what is JH, and JM here we define that is A, we substitute here. So the next step, we should find JH. Now look at these triangles, the cross-section area, the triangles JLK. In these triangles, we have another triangle that is right angle, and it is another right angle triangle. In these triangles, I name JH, this point, for example, is R, for example. In triangle JHR, this angle is 30 because all angle is 16, half of that means 30, 30. In these triangles, JH is the hypotenuse, and JR is half of A, or A over 2. So cosine 30 is adjacent per JH. So cosine is A over 2 per JH, and cosine 30 is root 3 over 2. So JH should be A over root 3. Now we have JH and substitute here. So it comes and substitute here. And by calculations, we find that C over A, or this ratio, should be root A per 3, or 1.633. And it is ideal. Why we say it's ideal? Because ideal when that there isn't any free space, for example, here or here, and we considered A over equals to R. It is optimum. Because of that, we say it is the ideal fraction ratio. The next step, for finding density, we need the volume of the cell. For volume, first we should find the area, cross-section area, and after that find the volume. Again, if you remember that, we can consider that it's 3 parts. It's part 1, part 2, part 3, part 1, part 2, part 3, and all of them same area, means the total area should be multiplied 3 times 1 of this area. Again, it is part 1, part 2, part 3. So if we calculate part 1, we can calculate the total area too. In area of part 1, so S of 1, we need BC times, so S1, it is BC times AE, okay? AC is A, this angle is 60, this angle is 60, total 120. In this triangle, BC is A times cosine 30, and A is 2R, so it should be 2R cosine 30, or root 3 over 2. What is the S1? It is BC times AE, means 2R root 3 per 2 times AE. How much AE? AE again is A or 2R. Okay, it should be 4R root 3 per 2 and write in 2R root 3. But if you remember, I told that the total area is 3 times, is 3S1, 3 times 2R root 3, it is, and it is 2R squared. It is 6R squared root 3. So we find the total area. What is the volume? It's the total area multiply in height, and height is C. So area times C is 6R squared times C times root 3. If, for example, we assume that we have the optimum, so for the optimum fraction ratio, if we assume the ideal ratio C over A is 1.633, then C can be written at C is 1.633A, and substitute in the above equations instead of C here. So C is 1.633A, and instead of A, substitute 2R. And substitute instead of C in this equation, and find the volume as a function of R. What is R? Atomic radius. So it is 12 root 3 times 1.633 R cubed. Okay. Now we want to compute the theoretical density by this formula. Density, or rho, is mass of atomic in unit cell divided by total volume of unit cells. We know that the Na, or Avogadro number mass, is A, is atomic weight, but we are looking for the mass of N atoms. For example, for HCP, we know that N is 6. How much the atomic weight? The atomic of this cell, or the cell weight, should be Na divided by Avogadro number. Substitute here. N is 6 for HCP. A, for different material, we have different atomic weight. Avogadro number is fixed, is 6.022 times 10 to 23 atoms per mole. And for example, for magnesium, that we know that it is HCP structures, we have radius, and A is 2R. Substitute here, we find A, 3.209 times 10 to minus 8 centimeter. Atomic weight, 24.305 gram per mole. Substitute N6, A, Avogadro number, and V cell. V cell is this, yeah, instead of R substitute. And for C, it depends. If the ideal, it should be 1.633. Here, I substitute 1.6, for example. 1.6A, substitute that, and we derive the density as 1.73285 gram per centimeter cube. But in reality, the difference between our calculations and the real density is 1.738. It's about 1.43% difference. Is negligible, this error. Okay, hope this video helped you to understand the topic better. As a special thank you, I have created the free study guide with everything that today we talk about. That to get your copy, just find the link in the description. Your feedback helps me improve these lessons. Leave a comment if you have any questions, and subscribe so you will not miss upcoming videos on the crystal structures and density calculation. Thank you.